Hello, everyone. So last time we were looking at quantifiers, if you remember. Quantifiers. And also nested quantifiers. Now, this time, we want to look at the methods of proof. Okay, so how do we prove a statement? And which methods do we have, or which options do we have to prove a statement in mathematics? So before getting into that, first let me introduce some basic terminologies. So some terminology, theorem are, the basically important results let's say an important result that needs proof. Proposition is a type of theorem that is less important compared to a theorem. So proposition and theorem, I can say the main difference, both of them needs proof. The main difference is that proposition is minor, a minor type of theorem, which is less important and normally as a simpler proof compared to a theorem. Okay, so theorem, proposition, these are the terms that are commonly used in mathematics. So we also have another term called lemma. This is a result that also needs proof. And that needs proof. And is normally used to prove a theorem. So sometimes, when you want to write the proof of a theorem, the proof could become very long, maybe, for example, 10 pages or 50 pages. But if we can try to divide, divide the proof into smaller parts so that the reader can follow it more easily, that would be nice, and in that case, we can call each each part of the proof, and we can call it a lemma. So that lemma can be used to prove the theorem, the main theorem, or it can also be used in other contexts as well, normally. So lemma is also, so in this case, in the sense that it's minor, similar to proposition, but it's also the main difference with proposition is that it is normally used to prove a major theorem. And then we have corollary. So this is a conclusion, basically. Corollary in mathematics means conclusion. So a conclusion of a theorem or proposition that also needs proof. So basically everything that we said here so far, as you can see, it needs proof in mathematics. So in mathematics, we need to prove everything. The only exception is when we have an axiom. So axioms are the facts that, we just accept them as they are based on maybe some based on our intuition. For example, let's say in pre-calculus, you saw that, for example, if A is bigger than B, then A plus C is bigger than B plus C. So this one, you call it an axiom. Axiom means you don't need to prove it, you just accept it. But axioms, the number of axioms is very limited. In each topic in mathematics, we have only a few axioms, maybe, 2, 3, for example, axioms, and then we can prove everything else based on or using those axioms. Okay, so what I was saying is that in mathematics, we do not need to prove axioms, which are only few of them in each topic, but then we have to prove everything else using the axioms and using the definitions. Of course, for definitions also, we don't need to prove them. We can use them to prove theorems or properties, use definitions. But so basically theorems, propositions, lemma, corollary, these all have to be proved or need proof. Okay. Okay, now let's look at the methods of proof. So one method is direct proof. Direct proof. So how does a direct proof work in mathematics? So suppose we want to prove a conditional statement. Conditional statement of the form, let's say if P, then Q. So we know that a conditional statement looks like this, and we said that P is called hypothesis or assumption, and Q is called conclusion. Now let's say if you want to prove this, now we have, most statements in mathematics are of this form. There are some assumptions, one or few assumptions, and again, one or few conclusions. Now, one simple way to prove this statement is to start from the assumption P and then do some type of reasonings or calculations. And at the end, we have to reach our conclusion, which is called Q. Okay, so in direct proof, we start with the assumption P, and we try to reach Q by doing. Now that depends on the type of example, what we do in the middle. So we start with Q, we reach Q at the end. Now in the middle, what should we do? Well, that depends on the context. Sometimes we have to do some type of calculation. Sometimes we have to do some type of reasonings or use definitions, for example, right? So that depends on the context, are we talking about proving a statement, let's say in calculus or in analysis or in algebra or in number theory? So the middle steps depends on the context, but in direct proof, the all common property in all the direct proofs is that, you start with the assumption and you reach conclusion at the end. So let's say we try to reach Q by doing, let's say, some let's say, reasonings and calculations, etc. In the middle, let me say. Okay, so well, that's straightforward so far, but I want to emphasize on a very important aspect of proof, whether direct proof or non-direct proof. So what I want to emphasize is that if you want to prove that a statement is true in mathematics, you have to remember that you have to prove it in general. You cannot prove a statement by giving examples. So this is, I can say, maybe the most common mistake that I see in all mathematical courses that I teach. So the most common mistake is that let's say give a question in the exam. I ask students to prove a statement. Let's say, for example, I ask them to show that, for example, if A and B are two matrices of the same size, then, for example, and square matrices, let's say, then, for example, determinant AB is equal to determinant A times determinant B. So that's a typical question in, for example, linear algebra course. And then I see some students try to prove this statement by giving examples. They say, okay, take this matrix A and take this matrix B, and then we have this property. So, which is wrong. So giving examples is not a correct way to prove a statement. The proofs have to be in general, not with examples. Even if you provide 1,000 examples, still it doesn't worth anything. Yeah, it has to be proved in general. So let me give this one as a very important remark, very important remark. To prove a statement, and or your proof has to be in general and not with examples. Okay. But so this is in the case that you want to prove a statement, meaning that if you want to prove that a statement is true. But what about if you want to show that the statement is false? Should we still give a proof in general, or do you think in that case, providing examples would be enough? So, however, if you want to show that a statement or a property is false, then you need to provide one example called counterexample. Okay, so this is the most important thing that you have to remember in proofs. To prove a statement is right, or to prove a property holds, your proof has to be in general, not with examples. Even if you provide 1,000 examples, doesn't worth anything. But if you want to show that a statement or a property is false, even one example, even providing one example would be enough. So, and that example is called counterexample. Now, what is the important feature of the counterexample? So the counterexample So how can we construct a counterexample that, let's say, if you want to show that a statement is false? So the counterexample must have the feature that it satisfies the assumption or hypothesis, but not, it satisfies this, but not the kind, but does not, or I can say, but does not satisfy the conclusion. Okay, so the counterexample must satisfy the assumption, not the conclusion. So why do we say this? We can think about a daily life example. Let's say, let's think about an example. Let's say if I say, if you get a grade higher than, for example, 70%, then your parents will buy you a gift. So think about this statement. If you get a grade more than 70%, let's say in the college, then your parents will buy you a gift. Let's say if you, let's say I ask you, is this statement true or false? Let's say you say it's false. And you want to show that this statement is false. How would you show that this statement is false? Well, you would say, okay, this statement is false because, for example, in math 100, I got, let's say, 82%, but my parents did not buy me a gift. So you would give an example that meets the assumption, but does not meet the condition given in the conclusion, right? Because if you say, for example, I got, for example, 60% in physics 100, but my parents did not buy me a gift. So this example is not showing that my sentence is false, right? Because you didn't get more than 70% in physics 100. But if you say that I got 82% in math 100, which is more than 70%, but still my parents did not buy me a gift, so then this example shows that my sentence is false. So in order to construct a counterexample, we are looking for an example that meets the assumption, does not meet the condition given in the conclusion. Okay, so I'll give examples for all these. So let's start with one simple example here. Okay, so this is an example we want to show that if n is an odd number, then n squared is also odd. So we want to prove a conditional statement here. So please remember again, each conditional statement has an assumption. So how do we know what the assumption is? Assumption is the part that comes after the word if, or after the word let in this case. The assumption is that n is an odd number, and then the conclusion is that n squared must be also odd. Okay, so let me write down here. So assumption n is odd, Conclusion, n squared is odd. So if you want to do direct proof, in direct proof, we have to start, we said we have to start with the assumption and then do some type of reasoning or conclusion in the middle. And then at the end, you have to reach the conclusion. So we will prove this statement using direct proof. So we start the assumption. Assumption says n is odd, right? Assumption is n is odd. So please remember, one important thing in proofs is that in almost all proofs in mathematics, you have to use the definitions that are involved. Again, for example, in linear algebra, for example, you want to show that, for example, if T is a linear transformation, then, for example, T of 0 is equal to 0, let's say. So when you see the word linear transformation, you have to look at the definition of linear transformation. So if you don't know it already, you can look it up on internet, or let's say on your notes or anywhere. So my point is, you have to always use the definitions that are involved in proofs. So here we have the statement is mentioning odd number. So what is the definition of odd number? So this is very important, okay? So we start with assumption. Assumption says n is odd. Now, what is the definition of an odd number? Definition of odd number is any number of the form 2k plus 1 for some integer k. For some integer k, according or by definition of an odd number. Okay, so far we already used the definition of an odd number. Okay, so we started the assumption, we use the definition, concluded that n is of the form 2k plus 1. Now, please remember at the end, so when you're writing your proof, you have to always have in mind that what are you going to do, or what do you want to reach at the end? At the end, I want to reach my conclusion, which is what? Which is n squared is odd. So based on your goal, you can decide what you have to do in the middle, right? This also happens in daily life, right? Let's say, for example, you want to go from a college to your home, let's say. Let's say starting point is college, end point is your home. Now, what would you do in the middle? Well, in the middle, depends on what you would do in the middle, depends on your goal. Let's say if your goal home is in Surrey, for example, you would take the train towards Surrey. You wouldn't take, for example, a train or a sea bus, let's say, towards, for example, North Vancouver, right? Because it doesn't match your goal. So what you would do in the middle should match your goal. Now, my goal is to prove a statement about n squared, right? So what do I have to do in the middle? I already have n. I know that n is 2k plus 1. I want to prove a statement about n squared. So what can I do? I can raise both sides to power 2 in order to get n squared, in order to make n squared appear in my proof. So then I will raise to power 2. So then I can say n squared is equal to 2k plus 1 the whole squared. Now 2k plus 1 the whole squared, I have an identity for it, right? What is the identity for 2k plus 1 the whole squared? A plus b the whole squared. A squared plus 2ab plus b squared. So this is going to be 4k squared plus 4k plus 1. 2k, the whole squared is 4k squared. 2 times 2k is 4k, and 1 squared is 1. Okay, I found that n squared is 4k squared plus 4k plus 1. Then what should I do? Again, please remember at the end, I want to reach the fact that n squared is odd. So far, I know that n squared is 4k squared plus 4k plus 1. How can I show that n squared is odd? Again, I have to look at the definition. What is the definition of odd? Definition of odd, as we said, is, I just wrote it here, any number of the form 2k plus 1. If I want to show n squared is odd, so that means I have to show that n squared is of the form 2k plus 1. So it's just a simple algebra, right? So I have 4k squared plus 4k plus 1. I want to write this number as 2 times some number, could be k, could be k prime, right? Doesn't matter. 2 times some integer plus 1. Well, 4k squared plus 4k, there is a 2. I can even take 4 as a common factor. But because I want to ultimately write it as 2 times some number plus 1, I will take 2 as a common factor. So 2 times 2k squared plus 2k, and then plus 1. So this is of the form, let's say 2k prime plus 1 for some integer k prime, right? See, if k is integer, 2k squared plus 2k is also integer. So I still have 2 times an integer plus 1. 2 times an integer plus 1, again, by definition, means it's an odd number. So that means n squared is odd. Okay. So please remember again, see my proof, as we said, because I want to show that this statement is false. And say I want to show that this statement is true. My proof has to be in general, right? Not with examples. So when I give this in exam, some people say, okay, let's look at n equals 3, for example. 3 is an odd number, and then n squared would be 3 squared, which is 9, and it's also odd. So if you write this one as proof, it would be completely wrong, because you cannot prove that the statement is true with examples. It has to be in general. In general means what? Means I took an arbitrary odd number, and arbitrary odd number is of the form 2k plus 1 for some integer k. So I'm not specifying what k is or what n is, right? So n could be any odd number. I'm not specifying which odd number. So that means it's in general. And then I calculated n squared and showed that that's also odd. Okay, so let's look at an example. So let's say true or false, justify. So let's say if n is an integer not divisible by 3, not divisible by 3, then n squared, then the remainder of n squared when divided by 3 is 1. Okay, so how can we know this statement is true or false? Well, we know that if you want to show it's true, we have to prove in general, not with examples. But maybe, if you want to know a theorem or a statement is true or false, or even if you know it's true and you want to prove it, it's always good to think about some examples just to get an idea. Examples is not proof, as we know, but just to get the idea, especially in this case, we even don't know whether it's true or false, to find out, to guess at least whether it's true or false, and also to get the idea. Maybe we can think about some examples. Let's say, for example, it says, so what is the assumption? Remember, assumption is the part that comes after the word if. So n is an integer not divisible by 3. So let's think about a few cases. For example, 4, for example, is integer not divisible by 3. And then it says n squared, the remainder of n squared when divided by 3 is 1. So that's the conclusion. So then if this is n, then 4 squared will be 16, and the remainder of 16 when divided by 3 is 1. Well, that's true, right? Because 16 is 5 times 3 plus 1. So the remainder is 1. Well, another number not divisible by 3 is 5. Then 5 squared is 25. 25 has also remainder 1 when divided by 3, because 25 is 8 times 3 plus 1. Or other, you can think of, try more integers, and you will see that any integer that you consider not divisible by 3, then n squared will have remainder 1. So our guess, so far it's just a guess because we haven't proved, we just thought about some examples. So our guess is that this statement is true. So I can say we will show that this statement is true. So again, proof has to be in general. So let's think about arbitrary numbers. So normally when you want to provide a proof which is in general, we can start by saying that let, for example, x be a real number, or in this case, n be an integer, arbitrary integer, and not divisible by 3. So let n be an integer not divisible by 3. Then, okay, then in the middle, I have to do, remember, I have to do some reasonings or calculations. At the end, I have to show that n squared has remainder 1 when divided by 3. So n is an integer not divisible by 3, so I can write n as 3k plus 1, or n equals 3k plus 2 for some integer k. Well, why is that? This is because of, so using, so I can say recall division algorithm. If, let's say, b bigger than 0 is an integer, then every integer n can be written of the form n equals, let's say, mb, or let's say qb plus r, where r is bigger than equal to 0, less than b. So this is called division algorithm. If b is a positive integer, you can always write n in the form qb plus r. Q is called quotient, r is called remainder, and the remainder has the feature that is bigger than equal to 0 and less than b. Now in our case, B is what? In our example, B is 3, right? So I can say N is equal to 3Q plus R, and R is greater than or equal to 0, less than 3, namely, so which integers are bigger than or equal to 0 and less than 3? So only R equals 0 or R equals 1 or R equals 2. But if R is equal to 0, in this case, if R is 0, then N will be divisible by 3. Which is not possible. Which is not possible by our assumption. So that means R equals 1 or R equals 2. So that means N is equal to 3K plus 1 or N equals 3K plus 2. So let's look at what we have done so far. See, I'm doing direct proof. In direct proof, I start the assumption. The assumption is N is an integer not divisible by 3. Then my first conclusion is that N is either of the form 3K plus 1 or 3K plus 2. Then inside the bracket, I justified this. I justified my claim that N is either of the form 3K plus 1 or 3K plus 2. So why is that? I basically use division algorithm. Division algorithm says whenever you have a positive integer b, any number n, any integer n can be written of the form qb plus r. Q is called quotient, r is called remainder, and the feature of the remainder is that is always bigger than or equal to 0 and less than b. In our case, b is 3, so n is of the form 3q plus 1, or I call 3k plus r, doesn't matter. So let's say 3q plus r or 3k plus r, and r is less than 3, bigger than or equal to 0. And there are only 3 integers which are bigger than or equal to 0 and less than 3. And those are 0, 1, and 2. Now, if r is 0, so if the remainder is 0, you learn this in elementary school or high school, that if the remainder is 0, then we call n divisible by b, or in this case 3, right? If the remainder is 0, then n is called divisible by 3. But my assumption is that n is an integer not divisible by 3. So that means r cannot be 0. So if r cannot be 0, is either 1 or 2. So that means either n is 3k plus 1 or n is 3k plus 2. Okay, so far we have this, n equals 3k plus 1 or n equals 3k plus 2. I started with the assumption, I concluded this. What do I want to have at the end? At the end, I want to conclude a statement about n squared, that I want to show n squared has remainder 1 when divided by 3. So what should I do in this step? I already have a statement about n. I want to get n squared. What should I do? I have to just raise to power 2 to make sure that n squared will appear in my proof. Okay, so now raise to power 2. So n squared is 3k plus 1 squared, or 3k plus 2 squared. So just use the identity, a plus b the whole squared, 9k squared plus 6k plus 1. And this will be 9k squared plus 12k plus 4. Now I can take 3 common, plus 1. And in this case, This one, I can write it first of the form 9k squared plus 12k plus 3 plus 1, right? I can write 4 as 3 plus 1. Why did I do that? Because I want to take 3 out. I want to take 3 as a common factor. And then if I write 4 as 3 plus 1, then 3 will appear and I can take 3 out as well from this term. So then I will have n squared equals 3 times 3k squared plus 2k plus 1, or 3 times 3k squared plus 4k plus 1, and then plus 1. So this is of the form 3k prime plus 1, right? Of the form 3k prime plus 1, and this is of the form 3, let's say k double prime plus 1 for integers k prime and k double prime. Okay, so I showed that in either case, whether n is 3k of the form 3k plus 1 or 3k plus 2, in either case, n squared will be of the form 3 times integer plus 1, 3 times some k prime plus 1, or 3 times some k double prime plus 1. So in either case, the remainder of n squared when divided by 3 is 1. Because whether it's 3k prime plus 1 or 3k double prime plus 1, the remainder when divided by 3 is 1. Please remember this R here that we mentioned division algorithm, this R is called remainder. Any R which is bigger than or equal to 0 and less than b and is appeared in this equation is called remainder. Now here I have 3k prime plus 1 or 3k double prime plus 1, and 1 is less than 3. So this 1 is considered as remainder. So in either case, the remainder of n squared when divided by 3 is 1. Okay. Now, another example, let's think about a similar example that we provided here. But let's say if I remove the condition that says, so look at the condition, look at the assumption here. It was saying n is an integer and is not divisible by 3. And then we said n squared is has remainder 1. What about if I remove the part that says not divisible by 3? Do you think the statement is still true or false now? So let's look at this example. Again, true or false. Justify. If n is an integer, then n squared has remainder 1 when divided by 3. So if you remember, we said that the very first thing you can do in this type of examples, that you want to know whether it's true or false, and also to get some ideas, is to just think about some simple examples. My only assumption here is that n is an integer. So I'm allowed to consider any integer that I want. And then I have to look at n squared, whether has remainder 1 when divided by 3 or no. But the very first integer I can consider, let's say n equals 1. If n is 1, then n squared is 1, which has remainder 1 when divided by 3. Let's look at another case, for example, n equals 2. Then n squared will be 4, which also has remainder 1 when divided by 3. Next integer, let's say 3. If n is 3, n squared will be 9. And 9 has remainder 0 when divided by 3, right? 9 has remainder 0 when divided by 3. And there you are. We found our counter example. So once you find an example that meets the assumption, but not the conclusion, or that is considered as a counter example, which also verifies that the statement or the property is false. My only assumption here is that n is an integer. Well, n equals 3 is an integer, so it meets the assumption, but not the conclusion, because 3 squared is 9, and 9 does not have remainder 1 when divided by 3. So I can say that this statement is false. And the counter example is that n equals 3 is an integer, and n squared equals 3 squared equals 9 has remainder 0 when divided by 3. Okay.